Okay, so chapter 20, the conduction. Remember we talked about the power conducted through a surface, through certain medium, is equal to the conductivity of that medium times the surface area times the change in or difference in temperature over the thickness of that material. So we can write it down something like this. Let's say this is the material, and you have here the outside temperature on one end is equal to, this is T outside, or you can say T1, and then this is T inside. Then this could be a cup, for example. Right, and you're trying to see, well, okay, let's say it's a hot coffee, so how much heat flows towards outside? Or it might be that the inside is cold and the outside is hot and heat is flowing inside. So you're talking about how much heat is flowing through that material. So P is equal to the power, how much heat per unit time is flowing through that material. So there's the 3 units, watts or calories or British thermal units. A would be the meter squared, so the surface area of this. It's not the surface area that we're seeing here, but it's the cross-sectional surface area, like that. So you can say that surface area of the material. And then that's meter squared, or centimeter squared, or feet squared. Change in temperature is the temperature gradient between the outside and the inside. So that's always Celsius. And because it's change in temperature, it could be Celsius or Kelvin. And then the delta X is the thickness of the material. So it could be meter squared. Well, if this was in meter squared, then this would be meter. And then if this one was centimeter squared, this would be centimeter. And then it could also be feet. So depending on that, you have 3 different units for the K. K is the heat conductivity. So it could be watts per, and then if this was meter squared, this would be meter, so that would be just meter, right? That would go down to the bottom, watts per meter Celsius. Or it would be calories. Oh, so no, sorry, this has to be calories per second, because calories is a unit of energy, so calories per second. So calories per second per meter Celsius. That would be the other possible units. Or it could be, and this has to be British thermal unit per hour. Or BTU per hour meter or feet Celsius. Oh no, it should be Fahrenheit. So Fahrenheit. So if we're doing the British system, the change in temperature would be Fahrenheit. So it would be Fahrenheit. So now the next thing we can see is how do conductors add up in series and parallel. And we mentioned that the other day. So how do we add them up in series and parallel? So if we had a material made up of 2 separate materials, let's say, like that, that would be in series. So let's take that material, let's say the thickness of the cup, but let's say it's made up of 2 materials. So then you have here K1, K2. So this is 2 conductors in series. So then what happens? How do we determine how do they add up? So when things are in series, usually something adds up and something is the same. For example, resistors in series, R1 and R2, the voltage across them adds up, right? We say V1 plus V2 gives you V total. But the current across them is equal to each other, right? So we have I1 is equal to I2, which goes to I total. So then to determine how do the resistors add up, we use the equation that gives us the relationship between this and this, right? Voltage is current times resistance. So then I'm gonna say V1 is gonna be I1 R1 plus V2 is gonna be I2 R2, and then V total is gonna be I total R total. Right, and then the I1, I2, I total is gonna cancel. Then you're gonna get R1 plus R2 is R total. So resistors, electrical resistors in series add up such that the sum of the resistances is equal to the net resistance, right? So then how do those add up? So what adds up in this case and what is the same? So what we're gonna say is the power flowing through here is equal to the same power flowing through there, the heat power. It's heat energy, you can say, right? So whatever has to flow through here, it can't just stay there. It has to flow through there. So we're gonna say P1 is equal to P2, which is equal to P total. So that's kind of like saying the current is the same. Whatever current flows through here cannot just stop here. It has to also flow through there, right? So heat power kind of behaves like electrical current in that sense, right? And then what adds up is the temperature gradient, right? So if the outside temperature is something and the inside temperature is something, then the temperature gradient from here to here, delta T1, is not the same as the temperature gradient from here to here, delta T2. So then we're gonna say delta T1 plus delta T2 is equal to delta T3. So the temperature gradient behaves like the voltage. But if you think about it, at first it doesn't sound like, at first it sounds like as if the power should be more similar to voltage, right? Rather than temperature difference. But if you think about it in depth, you will see that temperature difference should actually behave like voltage, because voltage across the resistor is what drives the current to flow through it, right? If there's no voltage difference between the two ends of a resistor, current does not flow. So in reality, voltage difference should always be written like this. Delta V1 plus delta V2 is delta V total, right? The voltage difference across this plus the voltage difference across that equals to total voltage. So it's because of voltage difference that current flows. Well, it's because of temperature difference that heat flows, right? So this should play the same role that this does. If there's no temperature difference between the two ends of a material, no heat would flow, you see? So therefore, this is definitely behaving like voltage, therefore, you see? Then after you determine this, then you say, okay, use the relationship between delta T and P. So delta T1 is gonna be what? P1 times X1, right? P1 times X1. Instead of writing delta X1, I'm just gonna write X1. So X1 is gonna be the thickness of this one right here. This is X2. Okay, so P1 times X1 over what? So we're trying to solve for delta T1, right? P1 X1 over K1 A1 plus P2 X2 over K2 A2 is equal to P3 or P total X total over, right, K total A total. Then we look to see if we can cancel some stuff. Therefore, we can get rid of them, right? So first thing we can cancel is P1, P2, P total, since in series they're the same. This one, this one, this one cancels. And we might also have other stuff that are the same. So A1 is the surface area of this. Remember, it's not this surface area that you're looking at. It's the cross-sectional surface area that the heat has to flow through. So A1 is the same as A2, which is the same as the total area, right? So in that case, that adds up. So that cancels. So you end up getting X1 over K1 plus X2 over K2 is equal to X total over K total. Now, can you cancel the X's? That one, not really, because X1 plus X2 is X total So the thickness of one material plus the thickness of the other material is equal to the thickness of the last. With resistors, you don't have to worry about that because the resistance of a resistor already has the resistivity length and the area built into it. You see? So the length of the resistor already is built into the resistance. Therefore, in the formula, the length doesn't appear. You see? Whereas the K is independent of the length of the material. It's just the material. You see? So it doesn't have the length of the material or the thickness built into it. You see? So therefore, this one just, nothing cancels. It stays the way it is. But there is another variable that we define, I think it's called the insulation factor. We can...
Professor, I'm a little confused. So
Yeah.
you said that K is independent of the length?
Yeah, K is a little bit more like the rho, the resistivity rho of a material.
Oh, okay, so it depends on the material?
Only the material.
Okay.
Yeah, you see. And the resistivity is 1 over the conductivity. The K is the most similar to the conductivity because the higher the K, the better heat conductor it is. The better the sigma, the better electrical conductor it is, right? But resistivity is opposite of conductivity. Well, there probably is another material, another quantity that's 1 over the K. That's like, so if it's a good conductor, if it's a bad, then it's a bad insulator, right? So then they have defined something called insulation factor. So before we look at different R values, let's see how they're defined. This is kind of, okay, I want to first see the definition, then look at insulation factor. Wikipedia. Where's the simple equation here? Yeah, that's the equation I was looking for. R is delta X over K. Okay, so basically that's the simple definition. So basically it's like the reverse of the K. So now the R behaves like the resistance, but it's also got the length of the thing built into it, right? So that means the longer it is, the more insulating it is, the material. The thicker it is, the more insulating, and the smaller the conductivity, the better the insulators, right? So it's the opposite of what conductivity means. And it's got the length built into it. So that's the definition of insulation factor. R is defined as X over K, where X would be like saying the length of the insulator. So then what would be the different possible units of the R? Well, then you take the different possible units of the K, which was watt per meter Celsius. Then the possible units of R, meter squared over watt Celsius. The other one would be centimeter over calories per second per centimeter Celsius, right? So it would be centimeter squared over calories. Did I do that right? No, I did that wrong. Watt Celsius. Because this goes up to the top. And then this becomes centimeter squared over calorie. Then second Celsius. And then the last one becomes feet per BTU per hour per feet Fahrenheit. And then that one becomes feet squared times hour times Fahrenheit over BTU. So those would become the different possible units of the R. So because it's got an extra meter or an extra centimeter, right? It's got the length built into it. And now they're saying, well, what if we do multi-layers, right? How do the R value adds up when we do a bunch of multiple layers? Well then, if this is the equation for how conductance adds up, X1 over R, K1 is R1, right? Plus X over K2, R2. X all over K total, R total. Oh, so one of the reasons for defining R that way is it just kind of makes it more like the electrical resistance, R. You see? It becomes like R, so the heat resistance adds up. So if you have two heat insulators next to each other, they're gonna become better insulators. You see? Insulation is gonna add up. But conductance is gonna decrease, opposite. You see? So that's what they're saying. In calculating the R value of a multi-layered insulation, the R values of the individual layers are added. R value outside air film, R value brick, R value sheeting, R value insulation, R value plasterboard, R value inside air film. Whole. So now we could look at some of those other places where it gives us the actual R values of different materials. So especially when it comes to building materials, we want to have a big R value, right? So this is fiberglass. Insulation terms can be quite confusing to anyone outside the industry. If you've ever bought insulation for your house, you know that insulation with a high R factor is better. But what exactly does that mean? Do you know that the R factor depends on other factors? When it comes to buying more specific insulation products like removable insulation jackets for hot pipes, understanding the particulars of the three measures of insulation is key. In order to understand the well-known R factor, it is important to understand the factors upon which it relies. The K factor and the C factor. If you are seeking out the formulas to calculate these factors, check out our RC and K factor formula conversion table that lists all the formulas. Okay? So the K factor, let's see here. R factor. Well, the R factor is going to depend on the L and the K, but then the K factor, what they're talking about the K factor is probably just this thing. All right, the K factor is the bottom. And then what they say C factor, they probably mean the length of it. So, in other words, insulation depends on how thick it is, plus the K factor. So it's the divide one by the other. You see, the K factor of insulation represents the material's thermal conductivity, or the ability to conduct heat. You see that? So the K factor is just the top, just this portion. You see. So what's the K factor? BTU inches per hour per feet squared. What was my K? BTU per hours per feet per Fahrenheit. They're saying BTU inches per hour per feet squared per Fahrenheit. Oh, they did a little bit different. They're saying the K is BTU times inches per feet squared. See, but they didn't change the units. You could do that, as long as you have 2 units of distance. So this is what I want you to be able to read. It's the whole point of education. Go to a random website, be able to interpret what they're talking about, what they mean, and also the units are very important, right? So they didn't change the unit, it's just they'd rather do it as inches, feet squared than Fahrenheit, right? British thermal unit square inch per foot per Fahrenheit degree, so on and so on. If R factor is known, this easier formula can be used to calculate the K factor. Okay? How is the K-factor of insulation reported? Polyolefin insulation, elastomorphic insulation. The C factor. What is the C factor of insulation? So the C factor stands for thermal conductance factor. The C factor, like the K factor, is the rate of heat transfer through material. The lower the C factor, the better the insulating properties of the material. Okay. Okay, but finally we get to the R factor. The R factor pulls together all of the information of the other factors and makes it easy to judge the effectiveness of insulation. The R factor of insulation can be found most easily of the insulation factors discussed. See this stuff that they're putting here? How do I calculate the R factor of insulation? Hour, feet squared, Fahrenheit over BTU. Hour, feet squared, Fahrenheit over BTU. Well, that's exactly what I did, right? Hour, feet squared, Fahrenheit over BTU. So what they did is probably to say, they did the R is equal to inches, right? They did inches over BTU, inches, hour, feet squared, BTU, inches canceled, and then this one went up and became this. You see how they ended up with? They ended up with the same R factor units that we have. Okay. Okay, now it would be good to see an actual table. Let's look at an actual table. These got go a lot more in depth. Let's see here. Well, these ones are more going about, depending on where you live, the kind of R factors you need. So depending on where you live, like if you live in colder regions, you probably need better insulation. But they're more expensive too, you see. So we are in the brown zone, you see. And then the blue zone is this one here. They need better insulation. Okay, I think this was the kind of table I was looking for. Okay, so so the R value, how is it given? Fiberglass, blown fiberglass, the R value that you put in the walls is different than the attic. The wall fiberglass is a better fiberglass, bigger R value, right? Now, how are they given? This first column is in units of some number over inches. That means per inch of the material, that's the R value, do you see? So what they've done is they've said R value of fiberglass. Okay, so let's say you are doing the attic fiberglass. Attic. So then that would be what? Somewhere between 2.2 and 4.3 per inch. Okay, and then the R value of fiberglass in the wall would be 3.7 to 4.3 per inch. So that means the attic ones you can install all the way to that value, and then the wall, but it has to be at least 3.7. The wall has to be better, right, than the attic one. So then if, depending on what the thickness is, so let's say you put 3.5 inch thickness of fiberglass. So then what would that be? R value of, for a 3.5 inch for the attic. Well then, if you're, let's say you're using 2.2, then you multiply 3.5 by 2.2, right? 3.5 inches, because this is per inch of the material, right? So 3.5 times 2.2, that gives you, it's a simple, just linear equation. 7.7. And what are the units of that? Feet squared hour Fahrenheit over BTU. But the units of this guy, 2.2, is feet squared hour Fahrenheit BTU per inch. You see? Then, depending on how many inches thickness it is, you have to multiply it by inches to cancel that, and then you get the units of the R. You see? So then the R value of the, let's see if that's what they put. Yeah, you see 7.7. Then the other one is 3.7 to 4.3, so 3.7 for 3.5 inch wall. Then you take 3.7 multiplied by 3.5, then you get 12.9. Okay, well, let's do a simple problem based on that. Let's say you have a house that is just two materials. Did they give you another one? Okay, so let's just say you have two materials. The outside temperature, I'm going to work with now British system. If the outside temperature is, let's say it's a hot day, 80 Fahrenheit, and the inside temperature is 50 Fahrenheit. Let's say it's really hot. Let's say 90 Fahrenheit, and this is 65. So you would like to keep it 65, right? So how much heat is going to flow through that? So let's say you have 6 inches of fiberglass attic, and then 3 inches of fiberglass wall. I'm just using those two as my sample, right? Yeah, of course, that wouldn't be a realistic situation, but let's just say you have two materials. One is 6 inches of the material fiberglass that you put in the attic, the 2.2, right? And then you have 3 inches of the fiberglass wall. So what do we know? Well, their insulation factor adds up as R1 plus R2 is R total, right? So then what is R1? Well, R1, since it's not 3.5 inches, what do we have to do? We have to take 6 inches, then multiply it by this guy, right? 2.2 to 4.3 per inch. So we have to multiply it by the, is that the attic? Yeah, so the attic, so it would be 6 times 2.2. You see? So of course these numbers would have to be given to you on the test, you know, based on those values. Plus R2 would be this guy. So 3 inches of fiberglass wall. So then that would be 3 inches times that, right?